Good morning. Today we will discuss about Fraunhoffer diffraction at a single slit. So in the last class you have seen what is Fresnel diffraction and Fraunhoffer diffraction and the difference between these two. So in this class we will discuss the diffraction at a single slit, Fraunhoffer diffraction. This is only a qualitative analysis. So let's directly go to the topic. Here you can see the figure. Let AB be a narrow slit. This is a narrow slit of width A. So this width is shown marked here as A. A plane wavefront of monochromatic light of wavelength lambda is falling normally on this slit. So the plane wavefront is falling normally on this slit, that is in this direction. Okay. According to Huygens principles, each point on the wavefront behaves like a secondary source producing secondary waves. So these are plane wavefronts which falling normally on the slit AB. So each point on this wavefront produces secondary waves. Okay, so this slit AB behaves as an array of such point sources which are highly coherent. This is just like the situation of Young's slit experiment, where we have placed one source behind the slits, where the slits acts as two coherent monochromatic sources. Here we are talking in terms of wavefront, and we are using the Huygens principle to define the secondary waves from the plane wavefronts. Okay, here O is the center of the slit, and almost all the waves proceeding from the sources are traveling straight in a direction parallel to OP. OP is this. So this is slit and plane wavefront falling on the slit, and this is traveling in this direction. Here placed a lens in order to converge these beams. So here is the screen. This is the screen. Okay, so this is a line OP. So all the waves proceeding from this point sources of the plane wavefront are traveling straight in the direction parallel to OP, that is in the forward direction, and are brought to focus at P at the focal plane of the lens on the screen. Since we have placed a lens here, all this light traveling in this direction gets focused at the focal point of this lens, which we can see on this screen if we are placing a screen here. Okay, these rays are covering equal paths and are reaching at P in the same phase without any path difference. So here you can see that these rays which are reaching at point P, which is the focal point of the lens placed here, is traveling same distance. So there is no path difference between these rays which are traveling and reaching at the point P. Okay, so they interfere or reinforce constructively each other, producing maximum brightness at the point P. So we will get maximum bright point at the point P, since these are constructively interfering. Thus a bright band is obtained at P, which is the center of diffraction pattern and is called the central maximum. So a bright band is obtained at the point P, which is the center of the diffraction pattern and is called central maximum. So you get a central maximum at the point P. Okay, now we are considering another point Q. This is the point Q just above P, where the waves are reaching at an angle theta with the direction of OP. So this is the direction of OP. So these waves reaching the point Q is making an angle theta with the direction of OP. So this is the direction of OP, which is making an angle theta. Okay, now Consider that the waves are proceeding from the extreme points A and B of the slit and they are reaching the point Q. So extreme points means this is the slit AB. So if we are considering these extreme lines, that is the light coming from the extreme points A and B. So we are considering only these two rays for simplicity. So these are reaching here. After refraction they are converging to the point Q. Okay. AM is drawn perpendicular. AM is, so we are drawing a line A from A to this line. So this is perpendicular to this line. So beyond this line BM. So beyond this line BM means from this point onwards and this point onwards, the path travelled by these rays, that is this path and this path are same. Only this much distance is the extra distance travelled by this ray compared to this ray. So remember the previous situation which we were discussing in the Young's double slit. It is exactly similar to that. Okay. So BM is the path difference between these two ways. We can find out this path difference by considering the triangle AMB. If you are considering the triangle AMB, from this triangle we will get this is angle theta. So sin theta is nothing but BM by A, where A is the slit width. So we can write sin theta is equal to BM by A, from which BM is equal to A sin theta. Okay. So this is the path difference. So let this path difference is equal to lambda and the slit be divided into two equal halves, that is upper half OA and lower half OB, like this. That is, the slit is divided into upper half OA and lower half OB, and this path difference, let it be equal to lambda, single wavelength lambda. So the path difference between the secondary waves from A and O is lambda by 2. Path difference between the secondary waves from A and O. So what we have said just before is that the path difference between the light from A and B is lambda. So now what we have done is we have divided this slit into two halves, OA and OB, and we are considering the extreme points O and A for this slit and O and B for this slit, and now the path difference between the light coming from the extreme points of the first half slit A and O is lambda by 2. Let it be lambda by 2, will be lambda by 2 if this, for this slit, if the path difference is lambda, then for this slit, then for the extreme light rays the path difference is lambda by 2. Okay. Thus corresponding to every point on the upper half OA there is a point on the lower half OB, such that secondary wavelets from these points have path difference lambda by 2 or phase difference pi, and destructive interference takes place and the point Q is of minimum intensity. So what we are saying is that we have got the path difference between the extreme points of the slits A and B, which is BM, which let it be equal to lambda. Now what we have done is we have divided this slit into two half OA and OB. Now we are considering this first half of the slit and considering the extreme points of O and A. So the for this light rays the path difference will be then lambda by 2, because for the full width slit it is lambda, then for the half slit it will be lambda by 2, and a similar half slit is there at the downside. So for every point point on the upper half, there will be a point corresponding to that point from the second half. So the path difference for these two rays, for any two rays here, is lambda by 2, and correspondingly there will have rays from points from the slit OB, and for the and that also the path difference will be lambda by 2. The path difference lambda by 2 corresponding to a phase difference pi, that is 180 degree phase difference. So a wave reaching from here and reaching from here will be of 180 degree out of phase. So what will happen when it reaching here? This 180 degree out of phase waves reaching here will interfere destructively. So we will get minima at that point Q. Okay, so the point P will be of minimum intensity. If the path difference Bm is 2 lambda, then what we are doing is we imagine the path difference Bm is 2 lambda. Then also the minimum intensity is obtained at Q. So this is because the slit now we are dividing into 4 equal parts. So 4 equal parts means from 2 parts, and the secondary wavelets from 2 nearby parts have path difference of lambda by 2, and hence has a phase difference of pi, and again destructive interference takes place. So if this is if Bm is 2 lambda, if the path difference is 2 lambda, again we will get minimum intensity at the point Q. In this case what we are doing, we are dividing this slit into 4 equal halves. 4 equal halves means for each quarter part the path difference will be lambda by 2. So for each wave from the quarter part of this slit, correspondingly there will be another part from the second part also. So then again this will be a situation of the previous case, that is interference of waves of phase difference 180 or pi. So we will get minima at the point Q. Okay, so we will get minimum intensity on the screen. In general, we can say that whenever the path difference, which is a sin theta n suffix n, is equal to n lambda, that is first we have considered lambda, second we have considered 2 lambda, so we can generalize it as n lambda, the diffraction minimum are produced, where n varying from 1, 2, 3 etc., and where theta n is the diffracting angle. Okay, so Bm is equal to a sin theta is the path difference. Whenever it is equal to n lambda, we will get diffraction minimum. Okay, now for n is equal to 1, a sin theta is equal to lambda. This is the first order minimum intensity. The first order minimum is also obtained just below P at theta 1 with the same angle of diffraction, just below P. Okay, the same angle of diffraction. Similarly, we get second order minima, third order minima, etc. for n equal to 2, 3, etc. The angular position of minima is given by, from this expression we will get sin theta n is equal to n lambda by a. So for we can find out the angle for varying value of n. Okay, since theta is very small, we can write sin theta n as plus or minus. So then if theta is very small, then sin theta will converge to theta n, then which is equal to plus or minus n lambda by a. So we will get minimas above and below P. That is why the plus or minus sign. For n equal to 1 it will called first order minima, and n equal to 2 called second order minima, etc. So also if sometimes the first order minima will be here, Q will be the first order minima, and another point on the screen will give you beyond Q will give you the second order minima, and another point beyond that the second order minima will give you third order minima, etc., etc. Okay, so we will get a central bright point and second different order minimas beyond this on both sides of this central bright point. Now the condition for secondary maximum. So the first maxima occurring at the central point. Central point is maxima. Okay, central bright maxima. Now the condition for secondary maxima is if the path difference Bm is 2n plus 1 lambda by 2. Then if this is the situation, now we can divide the slit into odd number of equal parts. Then the secondary wavelets originating from the two nearby parts have path difference of lambda by 2, and the disturbance produced by the secondary wavelets from two nearby parts cancel out, but one part contributes, and consequently maximals decreasing intensities are observed. So how this is achieved? So the condition for secondary brightness, secondary maxima is obtained by imagining Vm is equal to 2n plus 1 lambda by 2. 2n plus 1 lambda by 2 means the path difference is or integral multiple of lambda by 2. Okay, so in that case we can divide the slit into 3 equal halves. If we divide it into 3 equal halves, then only it will be equal to a path difference of a multiple of lambda by 2. Okay, because 2 equal halves will constitute lambda, and one more such part will give you an additional lambda by 2, so that will give you a lambda by 2 path difference. That is a multiple of lambda by 2 path difference. That's why we are dividing the slit into odd number of equal parts. Okay, so in such case what happens is, if you are dividing these into 3 equal parts, for each point corresponding to first part, there will be corresponding point from the nearest second part. So they will destructively interfere, and we will get minima, but there is another one more part there, because we have divided it into 3 parts. So from that part we will get a bright point, that is a distribution of light on the screen. That's how we get a maxima on the screen. Okay, so the condition for maxima is given by a sin theta n, which is equal to 2n plus 1 lambda by 2. A sin theta is the path difference, and the condition for brightness is 2n plus 1 lambda by 2 we have taken, wherein varying from 1 to 3, etc. So from this we will get theta n is equal to 2n plus 1 lambda by 2a. In the case theta is very small here. Okay, so if we are substituting for n is equal to 1, 2, 3, etc., we will get theta 1 as 3 by 2 lambda by a, which is in fractional form 1.5 lambda by a, 5 by 2 lambda by a, 2.5 lambda by a. Okay, let PQ is equal to x. PQ is equal to x, that is this distance, that is from the central bright point to the first order minima. This is taken as x. If the lens is very near the slit, or the screen is far away from this lens, then the distance between slit and the screen can be taken as the focal length of the lens. So what we are saying is that if this lens is very near to the slit, or the screen is very large, at very large distance from the lens, we can imagine the distance OP as the focal length of this lens. That is, imagine this lens is very near to the slit, that is, it is placed very close to this slit. Then the focal length is the if this is the position of the lens, from this point this distance will represent the focal length of this lens. So if this lens is near to this slit, then since these are very close, that is, the lens and the slit are very close, in such a situation we can take OP, the distance OP, as the focal length of this lens. This is only because these two these two slits and lens are very near or very close to each other. In such case we can take OP as the focal length of this lens. Okay. Now sin theta can be written as from such an approximation we can write sin theta is equal to x by f. Okay, where we can see from this figure sin theta. So this is theta. Sin theta is equal to x by f, because we are considering this point. This is an enlarged or exaggerated figure, so this distance and this distance is almost equal. That's why we are taking sin theta as x by f, that is the distance between the source and the screen as focal length. Okay, so we can write sin theta is equal to x by f. But sin theta from the previous expression we can write lambda by a is the condition for first minima. So we have got it here. Yeah, sin theta is equal to n lambda by a. For n is equal to 1, this is sin theta. This is sin theta, which is equal to lambda by a. Okay, so if we are equating these two, we will get, because left side is equal sin theta, so we can equate these two. So we will get theta is equal to sin theta is equal to theta when theta is very small. So x by f is equal to lambda by a, or x is equal to f lambda by a. Okay, where x is the distance of secondary minimum from the central bright point P. Since the secondary minimum is produced on either sides of P, the width of the central maximum. Okay, so we will get first minima here and first minima here. So this is the distance x that we have calculated here just now. So the width, so from the central bright point, this is the first minima on one side and this is the first minima on other side. So up to this point, this is the distribution of central brightness. So the width of the central bright point is this distance from Q to Q1. This is nothing but 2x. Okay, so 2x is equal to, from this expression, 2f lambda by a. So the intensity distribution of this diffraction at a single slit can be drawn here. So the central bright point will be obtained at the central point, and we will get first central minimum at lambda by a, and another second order minimum at 2 lambda by a, third order 3 lambda by a, etc. on one side, and on the other side and the negative side at these points. And we have seen for theta is equal to n is equal to 1, 2, 3, etc. the theta varying from 1.5 lambda, 2.5 lambda, etc. So for 1.5 lambda corresponding to the second order maximum, and 2.5 lambda by corresponding to third order maximum, etc., and similarly to this left side. So this graph represents the intensity distribution of the diffraction due to a single slit. This is the Fraunhoffer diffraction. The single slit diffraction pattern is easily observed in your daily life. Sunlight streaming through the narrow space in a window shade, a distant street light seen at night are some of the examples. So these are the examples from daily life. So this is about single slit Fraunhoffer diffraction at single slit. Okay, thank you.